for the survey. He's been here since July 2021. He's had a pretty full career so far as a researcher, entrepreneur. He's done a consulting work. He initially did his undergrad as a pre-med chemistry major at University of Illinois, but then he got a BS and an MS in geology there. He found that rocks were more fun than medical stuff, I guess, or chemical stuff, I guess. But looks like he's picked up the radioactive part of it here. But he completed his PhD at University of Southern California, and his complete bio, except for he's kind of a clay mineral geek that I understand, and a potter. So he makes pottery stuff. That's what that means. Adam, welcome. Thank you for coming to share with us.
Yeah. Well, first off, thanks, Kent, for the introduction. And, thanks to all the HAGS officers and Al and the survey for putting this all together and having me up here to pontificate about my dirty habit of chemistry or something like that. So, as you can imagine, old habits die hard. So even though I'm a geologist, chemistry still has an appeal to me. And hopefully after tonight, maybe you too, no promises. But hopefully by the end of the evening, you'll at least understand what this goofy diagram I have up on the screen is. But no spoilers for now. We'll get to that when we do. Quick shout out to the Pennsylvania Geological Survey's PA Geode. So, I know folks here, of course, probably are well aware of our data and map repository. Folks online, maybe not so much, but search PA Geode, hold your phones up to the QR code in the next 3 seconds or so, whatever suits you. But if you're ever interested in Pennsylvania data, maps, geology, we're your people. So to start you off, a picture explosion. Isotopes are used for basically literally anything you can think of in geology, astrogeology, biology. Just a minor sampling of things going on here. We have rocks and minerals, caves, corals, a token graph, zircons. This palisite in the bottom right corner, if you're not familiar with palisite, this often comes from meteorites found 6 feet underground in Kansas, but represent the core mantle boundary of a planetoid. So we've learned a lot from these things to try to understand how our own Earth was built. This all said, isotopes are about as overwhelming as this picture. So, and it doesn't help that, geochemists don't have an aversion to plain English. So I'll do my best here to try and translate from my goofy jargon to something a little bit more reasonable, but please forgive me if something may go over your head. But I mean, that's why this will be hosted on YouTube. It'll drive up the viewership. We'll get more views if you go back through and listen to every word I have to say, right? So, all right, first off, what are isotopes? Also referred to as nuclides. Every element is defined by the number of protons it has, protons being a positively charged particle. So the diagram I have here up on the left just shows different isotopes of hydrogen. Hydrogen has one proton, and that's the defining characteristic of hydrogen. The second particle in the nucleus is a neutron. Neutrons have neutral charge, and basically they exist to kind of stabilize the nuclear structure. So, we don't have things catastrophically decaying or becoming radioactive. We can live on Earth safely, so to speak. So in the case of hydrogen, hydrogen has 3 different isotopes that are stable or relatively stable. Tritium is sort of a special case. They're defined by how many neutrons that are present. So the first one on the left has 0 neutrons. Next one has 1, next one has 2. The systematic way of identifying these things, at least in isotope land, is to refer to it, the element's name and the number of total particles. So the one on the right, we refer to that as hydrogen 3, and we represent it with a label with a small number followed by the symbol that you see on the periodic table. So 3H or 54Fe would mean iron 54, etc. Isotope, I guess, is kind of a dated term, so to speak. It was more or less, it came to be, I think, in the 1920s, if I recall correctly. Modern particle physicists and such would use the word nuclides to sort of describe all the different isotopes that are available, to study. We were kind of hinting about this before while we were talking before the talk. How did all these different isotopes come to be? Lots of different ways have been identified. This will change, honestly, like it's changed already since 2008 when they discovered that a lot of the heavier elements on the periodic table, the stuff on the bottom half, were actually merging neutron stars as compared to supernovas, like really approachable things we have on Earth, right? But point of this diagram is we have a pretty decent understanding of where all matter has come from over the course of the universe. And we can use this idea to understand how it came to be and how these things might have partitioned through different meteorites, or the Earth as it was formed, or the moon, or a Pluton, or a coral head. So don't focus on this part too much. We'll get to it soon. So to create all those atoms and ions and elements, first we have to start off with a bunch of hydrogen. So hydrogen was the first thing that was in existence in this universe. Hydrogen is just a proton, no neutrons. In the early parts, there was a lot of energy, so all these hydrogens collided with each other in a sort of probabilistic way. When they collided, sometimes they combined, so they fused together. And when they did that, oftentimes, energy would be spit out, as well as small particles like neutrinos, if you've ever heard the word before. In this particular case, two hydrogens slam into each other. They form deuterium, or hydrogen 2. Combine that again with more hydrogen, you get helium-3. Combine helium-3 again, you get helium. So you keep adding hydrogens, and you keep adding more energy to the system, you create more different forms of matter from that. So all of a sudden, through this process, we go from hydrogen all the way to helium. Neutrons are a wily beast, so to speak. They can decay into protons, so transmute that matter, so to speak. This happens to some degree during this process, but also later on when we're dealing with heavier elements. Ooh, what happened? Wrong button, I'm sorry. Okay, yeah. So we get 4 hydrogen atoms, they combine to form a helium atom. Lots of energy is released, and after about 20 minutes after the beginning of the universe, we have a universe that's 75% hydrogen, 25% helium. This whole process is important because this is what people are talking about when they're saying nuclear fusion. So, we're talking about fusion reactors that they're building in England, as well as efforts that are happening in the United States. This is what they're trying to do. They're trying to combine this hydrogen into helium to release a ton of energy. It turns out, of all these processes, it's the last one, when the two heliums collide with each other, that produces a ton of energy. The units are mega electron volts, but that's relatively meaningless outside of a particle physicist. But essentially, creating one atom of helium-4, just one atom, is 18,000 times the energy of burning a gallon of gasoline. So this is why we're interested in this. Like this is why we're targeting this as a process to turn our world into Star Trek land, where we don't need energy anymore, and everyone's happy, so to speak. You may also heard in the news, I think it was probably 10 years ago, like Buzz Aldrin was making a big deal about, we need to go to the moon to find helium-3. And, most people would look at this and say, okay, we're going to go to the moon and mine something. Sounds great. Well, what he was after was that last step of the process. If you can collect a bunch of this stuff, which is exceptionally rare on Earth, free source of energy, you don't have to go through the upper processes, which are kind of complicated to confine because you have a giant hot ball of gas, the temperature of the sun, that you're trying to combine into a tiny tin can to create these reactions. So hydrogen, helium are in the universe. After a while, it gets flung off to the edges of the universe. The diagram in the top left represents sort of background radiation that astronomers have measured. Basically, what that's trying to show is that's where the matter was right after the beginning of the universe. It was spread out into splotchy bits, wasn't distributed evenly. This is important because gravity clumps those red areas together to form galaxies. If it was evenly spread out, there wouldn't be enough matter together to grab it to form those. So after 150 million years after the start of the universe, that's when we start seeing galaxies. That's when we start seeing stars form. A big linchpin behind all this is that it's really hard to get past helium-4. When you have two helium-4s collide together, they can actually combine and form beryllium-8, a different element with 8 particles. But this thing lasts like 10 to the negative 16th seconds. So that's like winning the Powerball twice, in an instant or something to that effect. Relatively impossible, but if you have all that gravity pulling everything together, you got a lot of matter, you got a lot of stuff hitting. Suddenly the odds are in your favor, and this happens. But once you form that, what you have to do is collide another helium with it to stabilize it. So, all right, you create this beryllium, it's stable for basically no time. If you combine it with the helium, it turns into carbon-12. This carbon-12 is often really stable, but the catch with that is every time that reaction happens, only 1 out of every 2,000 actually stays as carbon and doesn't just completely fall apart. So you have a whole process here that's exceptionally hard to get through, especially at the beginning, like at the Big Bang or something like that. You need a lot of mass together, clumped together to form this. A star is a wonderful place, tons of mass, lots of heat, lots of particles colliding with each other. So after you get through that prohibitive part, then you can start creating a lot of mass. So this is called the carbon-nitrogen-oxygen cycle. And what you're looking at here is you start with the carbon up on top. All you have to do is add hydrogen to it and just keep adding hydrogen to it. And you can create things like nitrogen, carbon, nitrogen, oxygen, and another form of nitrogen. So point of the story being, all you need is carbon-12. Then you can start creating the rest of the periodic table just by adding hydrogen to it, which in a star, there's a lot of. This is also why carbon is extremely abundant, at least in our solar system. So you have a star, it's burning, it's fusing the hydrogen and the helium on the outside. In the inside, it's forming carbon because of that process, because gravity and everything is pulling things together. If you have an even larger star with even more mass than our sun, which there are a lot of stars like that present, at least in our galaxy, you can start fusing all the way up to iron. And this happens in shells. So hydrogen is fusing the helium on the outside, helium is fusing the carbon in the middle, magnesium is being formed even further, silicon, and then iron and nickel in the middle. So kind of slightly different diagram, probably not the world's best because it's not representative of what's happening. You see the shells forming with iron forming in the core. Why it forms this way is, you have to have a lot of energy for these elements to exist. Each shell, as you get further in, is denser and denser, so more matter is able to interact with each other. But at a certain point, you just run out of energy. Like up in the hydrogen helium area, you're generating a ton of energy by combining it and fusing it. As you get down towards iron, you're generating less and less and less. So, that's why people are focusing on hydrogen fusion as a power source and not like trying to fuse silicon or something to that effect. So within the star process, you can't get beyond basically 56 particles, be it neutron or proton, before basically the system stops. Now, in between all this is where we generate everything in between those elements listed. So, a series of 24 or so elements. In a really big star, when it destabilizes, it forms a supernova. So what happens is that core gets so dense that it basically just implodes on itself. When it implodes, it creates a shock wave. That shock wave ripples out through the rest of the star and blasts away all those shells. So when that happens, you're left with a dense core of iron or so. Sometimes it gets denser. That iron degenerates into raw neutrons, forming a neutron star. Sometimes it doesn't. But in the rest of the supernova, you have the blast wave carrying all kinds of matter that's been ripped apart. So, every element between hydrogen and iron, as well as a lot of neutrons. Those neutrons aren't stable and they're flying all over the place. They're very energetic. they collide with all the other matter and basically produce the rest of the periodic table. So if you have iron, the heaviest element available, shove a bunch of neutrons in, that's when you could start creeping up to, copper and gold and lead and things like that. The rest of the hydrogen, the rest of the helium, and all those other new elements that are created by the star, they scatter into space. Eventually, they clump together to form a nebula, which then, kind of known as the stellar nurseries where new stars are being born, and it reseeds the whole process. So you create a new star, except now this new star has all the other elements in it, like iron and cobalt and, heavy elements. And you keep doing this for another 10 billion years. You generate enough mass to then basically fill out the rest of the periodic table before things start radioactively decaying. All right, so we've got a periodic table. This is a very complex version of the periodic table. It's called a chart of nuclides. And there's fellows out of the Australian National University that put together a nice web forum, or like a web navigator for this, that you can change all the colors. And it's probably the most accessible for those geeks that are deeply interested in something this heavy. But what you're seeing here basically are all the nuclides that can be created in the process of both supernovas, but also human-made. So everything that's in gray is stable. It won't decay, it won't decompose. That matter will stay the same until something is imposed on it. But it stair steps up because of the whole supernova process, because of the neutron star process, because of all those hydrogens adding into it. So I guess, how do you actively move up this table and go from things that are down in like cadmium in the corner, if folks online can see if that screen resolves well for you, up to like gadolinium up in the top right corner. What you're looking at here is just a little section of it. Basically, moving upward means in the process of whatever's going on, you're slamming protons, the positive particles, into it. Moving to the right, you're adding neutrons. So normally in a star, when it's going through that whole phase of, burning in the shells, there's free neutrons that are floating around because if you recall from the first slide, every time a hydrogen hits a hydrogen, it spits out a neutron. So there's free neutrons floating around. It absorbs in the matter and basically creeps up the side. So all of a sudden, if you had a cadmium 110, which is here in the bottom left corner, add a neutron, poof, it becomes 111. Add another one, poof, it becomes 112. Add another one, poof, it becomes cadmium 113. But cadmium 113 is not stable. So what happens there? Basically, when you go up neutrons, it decays back to stable. Or if you add protons, it decays back. So if you add neutrons, what it'll end up doing is just, creeping back to a stable point. So going back to the previous example, we have cadmium 113 on the bottom left. It will decay into indium 113. Slam another neutron into it, becomes 114 indium. That's not stable. Decays to 114 or tin. And this happens all across the periodic table. And that's how you can effectively transmute matter. Back in the alchemy days, people were always trying to turn lead into gold. Well, they didn't know the power of neutrons. The benefit of being modern, I guess. But so little intense. My apologies for bludgeoning you with probably a graduate class on particle physics, but also a supernova, may I point out. So getting basically through all these processes, you can create a wide array of matter with different amount or relative amounts and abundances because of the star processes, because of the supernova processes, because of the combining neutron stars, things like that. We also do it experimentally in nuclear reactors and things like that to create things even heavier than exist on Earth. So plutonium is probably the best example. Everyone's heard of that. It's component of nuclear bombs, powers all Mars rovers and things like that. All of our plutonium comes from irradiation of uranium, doing the stair-step thing until it goes from uranium-238 to plutonium-241. All right, so that said, in the study of isotopes, you can lump it into a number of different categories, but the one I'm choosing for us today is stable isotopes versus radioactive. So the stable ones, those are the gray ones I was pointing out. Those are the ones that, if you have any familiarity with study, are the ones that you'll see most frequently. So oxygen 16, oxygen 18, nitrogen 14, nitrogen 15. Also down below, strontium 86, strontium 87, strontium 88. There's no decay of these things. They are stable. The only way to sort of alter the ratios of this are beyond, star physics. Radioactive isotopes, on the other hand, are very useful for geology because they are used to more or less time events. So we know how frequently these elements radioactively decay. If we can measure how much the beginning and the end are, we can get a good sense of how long a process took. So strontium's a pretty common one. Rubidium 87 decays into strontium 87. We know the rate of that. I think the half-life of it, or the amount, the time it takes for it to decay to half the parent amount, the original amount, something like 40 billion years. So there's a lot of both. We use that to time geologic processes a lot. That is a decay. There's a decay process that happens to create that. Same thing for strontium and neodymium, a also common way of studying rocks. This is an alpha decay where basically the samarium shoots out one of those old helium particles to become a stable neodymium down in the bottom left, and so forth. I'll be talking about stable isotopes, although I have a soft spot for the radioactive ones. I've done plenty myself, but it's topic for another talk, I suppose. So also, if you read the title slide and the promotional materials that went out, I harp on this idea of non-traditional isotopes, which it might be a little antiquated at this point. There's a lot of folks studying these things, especially over the last 15 years, so they're probably not so non-traditional anymore. But the reference of this is the traditional isotopes are hydrogen, carbon, nitrogen, oxygen, and sulfur. And I'm sure others out there can argue some are traditional or not, but we've been able to do these things for an exceptionally long time, in science at least, 60, 70, 80 years. These things are typically done with relatively inexpensive, for a mass spectrometer, devices, commonly used for a lot of things. Non-traditional, however, these were very difficult to measure until relatively recently. Things were invented, special mass spectrometers were invented in the 80s, and they really weren't commonly deployed until about the mid-2000s or so. And now I would have to say, every other major university probably has one of these on campus. So if that tells you the relative abundance of how this study has grown over the last 15 years. But basically, non-traditional is everything else on the periodic table. So my poison of choice has typically been magnesium isotopes, and that's what I'll be talking to you a little bit after. But there's folks doing all sorts of other stuff, and I've been fortunate enough to do a lot of the other elements as well. And these take a multi-collector ICP-MS. I understand that this is more jargon, get that back to the cat, of course, but specialized mass spectrometer that helps measure these isotopes in an accurate and quick way.
Hey, real quick, what's AMS?
Accelerator mass spectrometer. So people use that for carbon 14 mostly. Basically, you shoot it down a tube as fast as you can. Anyway, so yeah. Here we go, particle physics again. You couldn't escape it. So stable isotopes end up fractionating. This is why we measure them. The ratios change in a controlled way. This was what I mean by fractionate. So fractionate just means partitions from one bucket to another, so to speak. Typically speaking, and I know someone will probably scowl at me either here or online about stable isotopes generally fractionate because of phase transition. So if you have anything going from solid to a liquid, liquid to a gas, solid to a gas, etc. This is typically employed in climate studies and things like that, but all across the geological board, from cold stuff on the surface to core mantle boundary sorts of things. In the most simple way of trying to show this very complicated diagram, not all bonds between isotopes are equal. So oftentimes bonds between heavier isotopes of the same element are stronger in a sense. And we can plot it on diagrams like this. We call this, a number of different things, but this represents a 0-point energy if you're even remotely familiar with that sort of thing. But fact of the matter is, this trying to show that each bond has different strengths. So because each bond has different strengths, then it reacts differently. Some are easier to break. If it's easier to break, then it's easier to partition between solid and a gas. Solids are dense constructs of, of atoms aligned in a crystalline form. As it converts to liquid, you break those bonds, or they become a little bit more, wiggly, depending on what sort of liquid you're forming. So in each one of these processes, forming a gas, it's going to break the easiest bond. This will play in a second. More about fractionation, so partitioning between those buckets, like I was saying, it's exceptionally small, so we come up with our own complicated jargon to sort of rationalize this to ourselves. No, I'm just kidding. Instead of like measuring these partitions by percent, we measure them by parts per thousand. So the term is per mil, and it has this somewhat complicated symbol, which is just a percent sign with an extra zero hanging off the end to represent parts per thousand instead of parts per hundred. We often present this stuff as a relative fractionation to a standard. So we have something called a delta notation using the small Greek letter delta, and it's just comparing sample to standard. So we set a standard for every isotope or every element, and we set it at 0, so that there's no arguing about that. It doesn't matter how it's partitioned. We're just saying the international standard is 0, and then we compare everything else to that standard. So for people who work in oxygen, we use an oxygen standard. There's a number of different ones, and we report a delta value to show fractionation. And on the bottom, say in the case of oxygen 18, if we have a positive number, so like say +2 per mil, the positive means that the oxygen 18 is enriched, the oxygen 16 is depleted. On the other hand, if it's negative, that means 18 is depleted, 16 is enriched. So basically, whatever the number is it higher or is it lower? So in this case, 18. Here's where it plays in, and apologies if the resolution of this is not as great for those online. Evaporation, just simple evaporation, raining, as well as the uptake of water into plants and things, shows dramatic isotopic fractionation. So the diagrams on the top left and the top right are basically two of the same phenomenon. You have water that's in the ocean. We set standard mean ocean water as our standard. Water that was sampled across each of the oceans and homogenized into a vat. I think Woods Hole might do it. I don't quite recall. But as evaporation happens, as it changes from that solid to a liquid, it preferentially takes out the oxygen 16 because that's the easier bond to break. So the clouds right above the water are -10 per mil. It's light, so to speak. As it moves over distance and the cloud, evaporates and precipitates, the numbers change. So in step 2, as the water is as water is raining out, that it turns from sort of like a water vapor to a liquid. Water vapor in the cloud, liquid is the rain. In the process of converting to a liquid, the liquid is heavy, the cloud is light. So the cloud gets even lighter, the rainfall is heavier relative to the cloud. And you keep going through this process, and many steps away from the ocean, after enough rainstorms, rivers, and plants get involved, you get a wide diversity of isotopic ratios that you can then use for processes like raining or plant growth or snowpack formation or glaciers or groundwater or cave formation, et cetera, et cetera. I guess another thing to note on the top left, we can measure the isotope fractionation of oxygen in water. We can also measure hydrogen. So what's represented there in delta D is actually delta 2 hydrogen. Sometimes it's represented as D because it is also known as the term deuterium. What you see basically just off of evaporation and precipitation is there's a way larger fractionation in hydrogen than there is in oxygen. And that's just because it's a lighter element. The bond is exceptionally easy to break versus the heavy ones. So you start combining these systems, you get all kinds of bonus fun that comes out of it. Point of that being, the range of that fractionation changes on the mass. So the lighter the element, the more it goes. Up in the corner, the deuterium is -78. You don't get that high as you move further down the periodic table to heavier and heavier elements. There's also more complicated ways to fractionate just beyond evaporation precipitation. For those more interested in mineralogy, the coordination number of an element within a crystal structure actually matters. I won't get into it too detailed, but in a crystal structure, each one of these elements, ions, molecules of choice are touching neighbors to form a crystalline structure. And that bond isn't just between one atom and a different one. It's caught in a lattice. So there's a lot of partial bonds that happen in between. And depending on how many neighbors each one of these atoms has, depends how strong the bond is. What this means functionally is, at least for magnesium, like I said, my favorite one, certain minerals are heavier than others just by merit of how many neighbors there are. And the most functional thing is spinel. Spinel is probably the best mineral to show this because it's isotopically heavy relative to everything else. Most other silicates, magnesium has a coordination number of 6, so 6 separate neighbors in that crystal structure. So, it doesn't really matter between your silicates, be it, hornblende or olivine or something like that. And garnet's light. There's also fractionation that happens during redox conditions. So people who are interested in superficial processes, this is important. Magnesium doesn't have different oxidation states. It's always magnesium 2+. So I avoid this problem, but for those interested in iron, there's an iron 2+ and 3+. There's fractionation that happens there, and processes that use iron, you can trace it that way. To make things even messier, one of the major projects I worked on during the course of my studies was measuring how temperature gradients can affect isotopic fractionation. So our research group was very active in trying to study magma melting and how the processes would fractionate during that. So basically, long story short of this slide is we set up a capsule that was probably about 2 centimeters long or so, and filled it up full of andesite, so an intermediate volcanic rock, melted it, crystallized it in a temperature gradient, and we see crazy isotopic fractionation of it. So the hot end of this experiment ended up being -8, so relatively light. And the cold end ended up being -6, so less negative, so to speak. This is greater than the range of the Earth. So, obviously, this is not happening. We're not melting the entire Earth and creating these sorts of fractionations, but it's a process to keep in mind, especially when we're talking about deep Earth processes. This is all aided by liquid. Liquid in the form of melt helps move isotopic fractionation around, but it doesn't have to be magma. It doesn't have to be melt. It could also be hydrothermal, supercritical fluids, things like that. All right, magnesium. I've harped about it enough. I love it. For those not familiar with the trivia of it, take this to trivia night. Of course, it's the 8th most abundant element in the crust. It's 3rd in the mantle behind silicon and oxygen, so major player in the Earth's mantle. It's the 2nd most abundant positively charged ion in the ocean, and fortunate for me, or at least it gives me job security or something like that. Knowing how the isotopic fractionation changes between those different buckets is still being actively studied. We don't have direct access to the Earth's core, or really the mantle for that example. So we have to resort to mantle xenoliths, parts of the mantle brought up in various tectonic processes or igneous processes. But it's a relatively simple isotopic system. There's only 3 that we have to take care of. 24 is the major one because of the star forming process. It's 79% of the total isotope bucket, so to speak. There's a 25 and a 26. They are lesser. The standard actually is a Dead Sea magnesium metal. So, folks dredge magnesium salts out of the Dead Sea, and I believe this lab in the Netherlands, I want to say, designated it as the standard. So, they were the first ones to use it, so they got to name the standard. My interest in it is, based off of what I said before, it's a major rock forming element. It's number 3 in the mantle, as I was saying. It's the lightest weight of all the choices available, outside of oxygen, of course, which I do not focus on in this particular case. but it has a lot of fractionation. And this is important because we have very set instruments with very set controls on them. We have to be able to see this fractionation to understand whether it exists. So as you get further down the periodic table, it gets so small that it starts becoming complicated to actually see the process that's happening. So go for the latest one. It's arguably the easiest to measure. I'd also pick it because it's a major element in the stuff I'm looking at. There's going to be less contamination in it if it's making up 30% of the rock versus 3 ppm or something like that. And it's generally immune to the redox effects, like I was saying. There is a wide variety of fractionation on the Earth, but not in igneous rocks, which, you know, as an igneous petrologist, go figure, right? But as you get to sediments, carbonates, waters, things start to get a little bit more lively, as well as soils and river sediments and things like that. The reason that we couldn't do this in the past is using the old equipment before the fancy mass spectrometers, we had a 1 per mil precision on this. 1 per mil plus or minus. So that basically is the entire range of everything you see on there, except for some of the really light carbonates and waters. So people just didn't study it unless there was something exceptionally crazy going on, like in industrial processes where there's melting of metal and things to that effect. So it's only that high precision that we finally get to it. So our precision is something like 0.02 to 0.05, depending on luck in a lot of ways, and repetition and statistics. So because we have 0.05, then we can start chasing the differences between mantle CPX versus Lux or something to that effect. Also thematically, a lot of what I've worked on is trying to understand how magmas interact with the rocks around them. We have a lot of, at least in geology, we have a lot of diagrams about how volcanoes form and plutons, the residual parts underneath it form. But depending on who you talk to, it's just shown as a cut straight through the earth, like it's not interacting with anything around it, which these magmas interact with things around it. So we can use, and people know about this, we can use tracers to try and understand this assimilation, or rather this bringing in of outside rock into your melt. And oftentimes people use the radioactive ones I was talking about, rubidium, strontium, samarium, neodymium. You can study the rare earth element patterns of a rock to understand what processes it's gone through. A lot of folks use oxygen isotopes, but oxygen isotopes are very complicated because if there's any weathering that happens, water has oxygen in it and can do kooky things with it. Water has less magnesium in it than it does oxygen, just by the structure of H2O. One of the processes that got me curious back in the day was trying to understand why granitoids seem to have a slightly different value than the rest of most of the rocks. So granitoids are rocks that resemble granite, but aren't necessarily strictly the definition of granite. They have a heavy signature in this diagram kind of shown above that grayish line. And folks don't generally understand what does this. We know a lot of the processes of rock assimilation and magma intrusion, and none of the ones we know of can explain this. So I have proposed, and others have proposed, that perhaps bringing in some of the particular matter might be the cause of this fractionation. More on this. There also is an issue with this particular study that opened up this line of thinking, this isotopically heavy granitoids. They use biotite to represent the mineral mica biotite to represent a granite. It's not the entirety of the rock. So are we ignoring other processes to be determined? So to sort of test this hypothesis of why do we have these heavy granitoids, there's a series of, I guess, 4 projects I'll go through real quickly to represent what processes could be creating these isotopically heavy granitoids. They're heavy in magnesium, unsure about other systems at this point. So there's 3 options. One, are they heavy because we're slurping in some sediments or perhaps metamorphosed sediments into the rock and tainting the signature because of that? Another option is oftentimes when you're creating granites are highly evolved rocks, and they're evolved because they started off with a relatively primordial magma as they're formed down in a subduction zone. And it's often rich in magnesium and iron, but by the time it erupts and gets to the top of the surface, it loses a lot of those characteristics and becomes really concentrated in silica and very much less in magnesium and iron. So in the process of doing that, some say it's losing the mafic, the iron and magnesium rich parts, to create the less mafic parts, which are the granites. So I'm testing whether we're assimilating some of those to bring that signature back in or releasing some of them. And last thing, is it all just a surface weathering problem? Are we just collecting crappy samples and all the heavy signature that we see is just from bad sampling or unfortunate weathering? So generally speaking, the way I would prepare a sample is collect a rock sample how you normally would, cut off the weathering rinds to avoid any sort of issues with that. Rocks get crushed and powdered down to a standard small size, less than 250 microns typically. And we only need like 20 micrograms to measure. So we often dissolve more than this because it's very difficult to measure 20 micrograms, let alone 20 milligrams of a sample. So dissolve them all. Oftentimes these things are very difficult to dissolve because there's minerals that are resistant to typical techniques. So we use a container called a par bomb, which is just a stainless steel jacketed container that is pressurized by its own vapors inside. So we put a little bit of nitric acid and hydrofluoric acid inside. The vapors come in, attack all the minerals, and release silica from the solution that's formed. Then we store these things in Teflon because it's concentrated toxic soup, so to speak. So we have a rock or soil or sediment. Now it's fully dissolved, or at least we hope so. Some minerals are very resistant to this. So this is why we use the pressurized dissolution. To measure magnesium or any particular element, the best case scenario is to completely strip that element from everything else in solution. So you dissolve a rock, it's magnesium, it's iron, it's silicon, it's aluminum, it's take your pick. If you have an ore sample, there's all kinds of other things in there as well. But for ease, we like having at least a 95% pure sample. Obviously, the better you can get, the better your analyses will be. So we use a process of chromatography to basically selectively strip out any element of interest. So, if anyone has any lab experience from previous days, magnesium takes about 48 hours to separate out because it's very complicated. And a lot of what my more recent work is trying to streamline this procedure. I think we have it down to about 7 hours or so in an unpublished paper, but still working on that. 7 hours sitting in a lab is still a little tortuous, so to speak. So using this process of selective stripping, some elements stick to these resins that we use more than others, and the selective stickiness is what controls what comes off of this. There's also other techniques called laser ablation, where you take a carbon dioxide laser or an ultraviolet laser, depending on what you're using, and you zap a sample. Like you literally, zap a sample with a laser. It blasts away the material and it brings it up into a mass spectrometer. But the issue with that is you're blasting that sample exactly as it is. You're not separating anything from it. Everything goes in there. So there are issues with doing it directly from that. It's certainly easier than 48 hours of chemistry, but it comes with its own complications. So for most of my work, I typically do the solution procedure rather than laser ablation, just for well, it's the way I picked it, so to speak. These mass spectrometers that I'm referencing are very complicated pieces of equipment that basically take a sample. In this case, we measure samples that are 0.5 parts per million, so extremely weak samples. We put it into a radio frequency plasma generator. So we shoot radio frequency into it. It turns into a flaming ball of gas. We use that ball of gas, strip out all the ions that we're interested in electrically and magnetically until we create a beam of just what we're interested in by applying just the right magnetic field and just the right electric field to it. And we collect it in a series of cups in the top right called Faraday cups, which are just basically either pieces of carbon or pieces of copper. And these particles, all they're doing is slamming into a cup generating a charge, and we're measuring a voltage. So we have 3 separate beams in this case of 24, 25, 26 magnesium. They're generating voltages. We measure them with voltmeters, and we measure the ratios between the two. We do that because the absolute concentration of what's going in there doesn't matter. So the ratio is far more useful to us. And we apply different filters to it. So I write it up here in case anyone either here or online is interested. But we use a medium resolution. So this filter basically tries to screen out extra particles that go in. Because if we're trying to focus for 24 magnesium, sometimes molecules of carbon sneak in there because two carbon molecules, 12 and 12, add up to 24. It's the same weight more or less as magnesium. So we can apply filters to screen those out just because the weight is not exact. It's very different in like a 5th decimal place kind of way. So screen out all the extra junk as much as we can. And when we're measuring, basically we take a sample and we compare it to a standard, more or less immediately. So we call this standard sample bracketing, where you just bracket a sample with 2 standards. So standard sample, standard sample. We do this mostly just for quality control issues, and we get great precision and accuracy from doing it this way. All right, so first one are these granitoids formed by sediments. In Yosemite National Park, there are a series of intrusions that happen as part of the Cordilleran batholith in the Cretaceous, the Jurassic, and the Triassic. There's lots of intrusions going on there, and it's home of the relatively famous Tuolumne batholith. If you're you get subjected to that in intro petrology sort of classes. The big pink blob, the Tuolumne intrusive suite, is the thing that intrudes last. But as you can see, it's very complicated because there's lots of intrusions and there's lots of rocks that were pre-existing there beforehand. In a more detailed box in Yosemite National Park, if you're not familiar, is basically directly east of San Francisco in California. One little area on the edge of the Tuolumne batholith, as it's intruding in the host rocks or the rocks that were already present there, there's little slivers of metasedimentary rock that still exist that were not completely obliterated by the intrusion of a magma. We call these things pendants because they were presumably little pendants hanging from the top of this intrusion. Where they actually existed relative to the 3-dimensional aspect of this intrusion is still unknown, but the term is stuck. So all the colored rocks that you see on the map on the right-hand side that was part of a mapping project that I did represent different sedimentary rocks that were left over. The pink on top is a separate intrusion. The purples on the bottom are the Tuolumne intrusive suite that I referenced. So 2 samples that were taken from there. One is of a metamorphosed sediment, a metamorphosed sandstone and siltstone that I refer to as metapelite, and a granodiorite from the intrusion down below. What we basically see is the signatures on these on the graph on the left are significantly lighter than the rest of the rocks. If you look at the bottom of the graph, it shows the delta 26. You can generally ignore the delta 25 on top. We just put that there for different reasons that I don't have time to get into quite today. But the metapelite is sitting at negative 1.5-ish or so, and the granodiorite is basically negative 0.6. So that range is like 0.7. That's significantly high, especially for sedimentary rocks and for intrusive rocks. Both of these are lighter than bulk earth, so there is assimilation that's going on here. The granodiorite is assimilating some of this metapelite because the original probably is actually up on the top of that dashed line, up on the top right. So everything is being dragged down lighter to the left. So both this metapelite and this granodiorite is assimilating things, but they're being dragged light. I'm trying to look for the heavy thing. So assimilating sediments or metasediments probably is not the way that you're creating these heavy granitoids, because as I showed last, it's dragging it lighter. Not really going to work. Round 2, I looked at a pluton or intrusive body in the Smartville complex in Northern California. So in this case, basically directly north of Sacramento, about an hour or so. There's a series of intrusions, linear intrusions that collided into the North America at that point in the Jurassic, so part of the Nevada orogeny that supposedly exists. There are arguments about that. I'm not sure where the current literature sits, but this is represented to be an ophiolite or a sliver of oceanic crust. For those who are not quite familiar with what an ophiolite or what oceanic crust looks like, we basically see the structure in the oceanic crust preserved in ophiolites, and this is how we know what oceanic crust looks like. It starts with peridotite down at the base, and you see a bunch of gabbro above it. Often you see sheeted dikes, basaltic dikes that arise from the region of the gabbros, and you form pillow lavas at the surface as that lava approaches the ocean floor and hits water and forms domes that look like pillows, and deep marine sediments on top if you were in a location that had sedimentation. Combine this with island arc volcanism. So you have this section of oceanic crust, now shove a whole bunch of magmatism through it. Imagine there's a subduction zone underneath all of this, generating partial melts because of the water that comes off the subducting slab, generating a bunch of melts. These melts pond upward due to gravity, and they pond at different layers, like at the moho in the middle and various places in the crust. So oceanic crust, lots of plutonism, lots of intrusions that are happening at different layers. And the fact that these are happening at different layers is important to the next part. When you have each one of these bodies, crystallization happens. You know, you're not emplacing a giant pool of magma just as a giant ball of liquid. Cooling happens because this is intruding into other things that are colder than it is. So when that happens, oftentimes you get crystals that start forming in the melt. Sometimes due to density, they sink or float. And this has been argued quite significantly, depending on your field of research. But oftentimes, we at least see the parts that settle downwards. The floating can be argued, depending on where you're at. Conversely, on the diagram tilted off to the side, because I tried to cram too many things in the one slide, of course. Imagine a hot body of magma as it's approaching the colder outsides. Oftentimes, crystals will be growing along the outside on that cooler surface. And sometimes when this magma is moving around, it gets squished and pressed against this thing as well. So there's a lot of places to start forming crystals in a melt or in a magma or in a pluton or in an intrusion. Diagram down the bottom right tries to show this in a little bit more fine detail, but imagine igneous intrusion happens, crystals are forming. Eventually, you'll exhaust the amount of, you'll exhaust the ingredients for those crystals. So, you know, all the green crystals, there's nothing left for it to crash out. So a new crystal starts forming, the black ones. Once all those ingredients are gone or the temperatures aren't right, those stop forming and the white crystals start forming. So you can start creating things like layered intrusions from this. So the pluton that I was studying was conjectured to be one of these things in figure number 4, where it's a series of crystals that are forming in a sort of mushy magma, so to speak. The map of the top-down map of the pluton's off on the right-hand side. I sampled across it approximately a line across the axis of it from northeast to south, or sorry, northwest to southeast. And each one of these colored bodies represents a supposed layer among the little layer cake or tiramisu or so that I showed in the last diagram. So the goal here was to see, you know, is there any change in this? And it turns out within the errors that I was able to at the time, and this was a very early project, so there was techniques that weren't developed to hone this better than it was. The error bars shown within the box basically all fall within each other, and they all fall within the bulk earth values represented in the green bar. So even though this pluton was existing, perhaps in a temperature gradient, perhaps with a lot of crystalline processes going on, there's no fractionation in it. So this isn't really a good target for moving things either light or heavy. There, you know, a more modern analysis of this might show perhaps a line shown in red where there is a little bit of fractionation, but at this point, it's just a guess. Sample number 8, on the other hand, which confused me a lot, at the time, because, you know, it's very off axis. It's down probably 0.1 per mil or so. It's weathering. It took me 5 years to figure it out, but it's a very weathered sample. We grabbed out a very terrible outcrop. And what we're looking at is probably the effects of water and weathering on it. So these are mafic cumulates. These are well-defined mafic cumulates, like that diagram number 4 I was showing. Not necessarily what we're looking for. So looking at gabbros in yet another part of California, Joshua Tree National Park, if you're familiar. It's east of Los Angeles, probably about 3 hours or so. Dramatically more popular since when I started and now. So I'd like to think I had a small hand in that, of course. What you're looking at is what it's most famous for, just fields and fields of granite. What climbing heaven, and it's very approachable and very walk-offable, you know. But none of this is gabbro. Of course, I'm standing on the gabbro, looking out at the granite wonderland, or the aptly named Wonderland of Rocks, and you can see why. Here we have demonstrable host rock assimilation. We see it all throughout the less scenic parts of Joshua Tree National Park. So each one of these diagrams here is showing light-colored igneous intrusions intruding into host rocks and more mafic, more primitive gneisses, amphibolites, and igneous rocks. So down on the left, all those black chunks are being broken up, dissolved, and being reprocessed. You see it even more closely on the top right, where those black chunks are being basically systematically disaggregated and turned into a new sort of like Oreo cream smoothie sort of thing, like a homogenization of white and black crystals. So the gabbros I'm looking at, if you're interested in the technical details of it, they're porphyritic, there's large crystals in it. Very hornblende rich. It's a gabbro to diorite, so relatively primitive. It's known by mostly hornblende, plagioclase quartz, either diopside or biotite, and an oxide in there, usually titanium rich. There's upwards of 3 centimeter hornblende crystals in it. Very beautiful sample. And it's metamorphosed just to make things slightly complicated. So we get good epidote, good chlorite, but you know, nothing gemmy or anything like that. These things are complicated, and I can give a whole separate talk on this. Don't tempt me, but they're multi-process, complex cumulative. These things were formed by a lot of magma intruding, interacting with it, and growing larger crystals and it settling out. And analyzing these things, they're exceptionally light, so negative 0.6, whereas the bulk Earth is negative 0.3. So significantly lighter. The granites, even though they are interacting with this material, they're not assimilating it. If anything, they're reacting with it and depositing, if you want to think of it that way, a light signature. So these things probably actually more represent a residual material coming to create the granites than it is the granites doing something to it. So in the grand scheme of things, we're probably not assimilating these mafic bits as shown in the Smartville complex, the Pilot Peak Pluton, but we could be releasing them down in the crustal column as these things are migrating upwards due to gravity mostly. So the tiebreaker, so to speak, if you want to think of it that way, is it surface weathering? In southern Spain, just west of Malaga and north of Gibraltar, is a body of peridotite that was exposed because of a tectonic collision. There is a matching bit often in Morocco, just off the map, called the Reef Complex. Same process, different side of the ocean. But you see a variety of different mantle types there, which intrigue folks that are really interested in mantle. The 3 types are based off of whatever aluminous mineral is there. So the mineral that has aluminum, which isn't terribly high in concentration, but plagioclase is your option, spinel, or garnet. And those all vary depending on depth. So plagioclase shallow, garnet deep. And I was told to put a phase diagram in just to bore people to tears by a certain supervisor of mine. So I throw that in there in part that, but just to also show that those depths are a little bit wishy-washy depending on what temperature you have. But plagioclase peridotite is I guess, rock of particular interest because you don't often see a mantle that's that shallow. Like what mantle is 25 kilometers deep? The oceanic crust is, you know, arguably 7 kilometers or so, but we don't have access to it. continental mantle is far deeper than that. So collected 3 samples from each of the 3, well, 3 of the 4, I guess species or whatever zones of this peridotite. Wasn't able to collect any in the plagioclase peridotite for this particular sample because of lack of exposure and development and housing and things like that. But the thing you notice in the villages nearby, because there are a lot of small mountain villages that just kind of pop up throughout because, you know, they have a lot of history, of course. Hubrique up in the northwestern being a particular one of them, use these peridotites as paving stones. And they're extremely striking because you see basically a core rim texture to it, where you see cores of the rock in a nice, pleasing medium gray, the outside rusty orange color. So they use these decoratively on its path, on the side of houses, things like that. So what a great place to see whether weathering is a concrete event, because it's a very sharp contact. And the weathering rind is a very coherent body. It doesn't crumble. It's a relatively intact rock. So we don't have to worry about crumbling or water or things being present. So sampled a broad aspect of these, looking for core and rim, just represented by R with rim, C with core. I avoid the interface between the two just because 3-dimensionally it might be complicated, and you want to avoid any sort of issue with the phase, at least for this first pass. Crushed processed during doing the chromatography that I said. Looking at the bulk chemistry of these things, we basically see, above all, the cores have more magnesium than the rim. This is to be expected just because of water coming in and dissolving this magnesium. The fact that there's difference between the two also hints that there could be isotopic fractionation because material is being lost and things are being partitioned. Looking at these rocks in thin section, they're a delightful mess, but the difference between sample or the left one and the right one, the fact that you can see coherent blocks of color, so the yellow and the blue and the purple, show that there's still intact-ish olivine grains that are present. This hasn't been completely obliterated by weathering, but each one of these brown and clear and black veins are serpentine that's been formed either a long time ago or, believe it or not, recently. The weathering forms this serpentine. So, and the reason it's brown is because of iron oxidation. So part 2 of this was to be studying the iron fractionation, but we didn't get to that side of the project. So magnesium increases from the weathered part on the left hand to the original part on the right, which correlates with what I showed before, that the core had more magnesium than the rim. The weathering is yet another phase of serpentinization. This creates a whole bunch of extra iron that's free to stain this thing that brown. And what we see is a lot of enrichment and depletion as a consequence of this weathering pattern. Isotopically, it's a big mess, and it has stumped a number of people that I've spoken to. There may be a lot of issues that are wrapped up in this, but generally speaking, the rind is isotopically heavier than the core. However, 2 of the samples show one way, 2 of them show the other way. What this may be, and I tried to represent this with arrows, but it is still a data mess, and I apologize for that. But I think what's going on here is there's spinel in all these samples, and spinel is isotopically heavy. And if you don't dissolve all of the whole rock sample, then you might be tainting the isotopic ratio. Also, critters live in these things. It's a soil, and some of these have been sitting in soil. So biogenic activity, critters may be actually actively fractionating this thing heavy as compared to light chemical weathering. So add on top of this, on one of the original slides long ago, mantle clinopyroxene is actually relatively heavy, so around 0 as compared to bulk earth, which is negative 3.2, and some of these lighter things. So something happened in all this where I may not have dissolved all the sample because of that spinel, which is notoriously difficult to dissolve. These are essentially layered rocks of olivine and pyroxene. So is the rind different from the core by the amount of clinopyroxene that's present? I don't know, not at this point. So this was this ended up being far more complicated than I intended it to be. The results are muddled, and I'm not sure I can definitively say anything beyond, this is fascinating. So focusing on just the cores, just to try and remove the whole weathering story out of this. Bulk mantle is the green box represented by San Carlos, Arizona olivine. And one of them is slightly lighter, as represented by off to the top right. Majority of them are sorry, I must have said that right. One slightly heavier, the rest are lighter. So serpentinization probably created lighter values of this, because I wasn't sampling just the pure olivines, I was sampling the core of the rock, which is highly serpentinized. So serpentine also probably messed with all this as well. But point of the story is, these are all trending light, except for that one that arguably is pretty close to mantle. So weathered magnesium-rich rocks are basically trending to the right in some manner. So if magnesium-rich soils are trending that way, imagine what all the other ones are doing, probably about the same. So this is a grab bag. Basically, weathering rocks can go either direction. There's mineralogical controls. There's groundwater to be affecting in here. There's biology. So making any sort of broad brush statements using surface weathering of magnesium-rich rocks to try and understand how an entire batholith was formed was obviously an overstatement. But you live and you learn, right? So anyway, I guess my conclusions with all this is part one, before all the geology, yes, there's a lot involved in isotopes, and it's a wonderfully complex, wonderfully exciting field, at least from my perspective. You're welcome to disagree, but there's a lot to it. So my apologies if I'm overwhelmed, but like I said, go back on YouTube and start Googling some things or ask me questions, you know? And part two, in my quest to try and understand these isotopically heavy granites, oh boy, you know, there's a lot going on here. Like, are these granites actually heavy? I hinted at the beginning that did this guy preferentially skew his sample set by only focusing on the biotite parts of a granite? Maybe, maybe not. Did he sample weathered materials? We don't know. We will never know. If this is all just weathering, that still doesn't explain why is biotite heavy. Good question. What the more likely result on all of this is granitoids probably represent the heavy reservoir. So there has to be a balance. If there's a bunch of stuff that's light, there has to be something that's heavy to normalize it out. Or we pick the bad standard, which may also be the case. But if anything of the options I present today, it's probably forming those mafic cumulates. So forming those hornblende rich iron and magnesium rich horizons and tucking them away somewhere in the middle crust that's driving this. More obviously needs done, but to solve this problem. Metamorphism of sediments. These sediments, it's been understood that metamorphosing these things might not change the isotopic fractionation of this. We don't know enough about how metamorphism of a particular sample controls the whole system. So there might be issues involved with this, especially metamorphic rocks can form in hornfells or contact metamorphic situations where a very hot body is next to a very not hot host rock. Is there fractionation happening because of that temperature gradient and therefore skewing the samples one way or the other? Don't know. We have to go find a whole bunch of intrusions and a whole bunch of host rocks to study. So, and finally, there's a lot of issues with that last study, the one on the Roundup peridotite. I think the minerals are controlling. I think serpentine is affecting this more dramatically than I originally understood. So minerals present in a rock likely have more issues with fractionating isotopes than we understand at this point. Anyway, that's enough for me. Let me leave you with a little bit of an outer space to bring us back out to a larger view. I'm also leaving you with the Ph.D. QR code if you are interested in that, and my email address. Feel free to ask me questions. Like I said, I know this was probably a little overwhelming for a Thursday evening, but always happy to try and deconvolute anything I said today. But thank you.
Thank you, Adam. Any questions? We got some thanks and wows in chat.
Also accept tears and agony, but yeah.
Can you quickly re-summarize fractionation and heavy
Yeah.
and light? What could, how the fractionation causes heavy and light?
So heavy and light are just relative. So
Right, I understand
you
that.
like, you set a standard. The standard often is somewhat meaningless, or it could be meaningful depending on how the original person came up with it at this point 20-25 years ago. But different processes can either, yeah. So dragging or sorry, maybe I misunderstood your question.
Well, the heat fractionation
Oh,
causing changes in the
Yeah.
isotopic
yeah. So
ratios.
So there's diffusion that happens along temperature gradients, and it's been studied, I think, since French man Sauret came up with it, I believe in 1908 or something around that, where if you have something in a temperature gradient, stuff migrates along it. So like in our little capsule, we started off with an andesite, a homogeneous andesite, and all the heavy mafic stuff, the iron magnesium stuff, like fell to the bottom, and all the light stuff basically floated to the top. So in the process of just that physical separation, there's also crystallization happening, as well as melt moving around and touching all of the crystals that are being formed. So in that, the light materials floated to the top because they were easy, the bonds were easier to break, and the heavier stuff sank to the bottom and also kind of got sucked up into the crystals that were there.
Okay.
I don't know if that makes more sense or if that confuses further, but it was a complicated experiment because there was a little extra like drama that happened with some of the crystals in the middle, but generally speaking, they've replicated that experiment a number of times to show generally in a hot zone, it's isotopically light, and in a heavy or in a cold zone, it's isotopically heavy relative to what they started with.
Okay.
And I guess the cool idea with that is imagine that happening over and over and over again, like 1,000 times in the crust. That's when you might actually start partitioning out this light granites and those heavy cumulates. At least that's the idea behind it.
Because I was.
Sorry.
Go ahead, Bill. Maybe I missed this, or maybe I'm not quite clear on the concept.
Yeah.
But are the different isotopes of any particular mineral differently soluble in water, particularly under geologic circumstance, that is, in the crust?
Yeah, I mean, there definitely is water controlled fractionation that happens. And there's a lot of groundwater studies that show this. Like oftentimes they use these things for contaminant plume. So we were working on a particular project out in southern New Mexico that was studying a cadmium plume. And you could see that just in the process of it migrating down the, subsurface plume boundaries, there was fractionation that was happening from the source all the way down.
Was it getting lighter or heavier?
I believe it's getting lighter, although it's been a while. But you can also then use these things to sort of retrofit the source to some degree, but that's slightly more complicated.
Prototypes, it sounded like they were prized for architecture because of the contrasting color. And it made it sound like the core was pretty like stable or solid. But I'm curious, like over time, did you see any of them where that contrast is like starting to go away? The interior is letting out some iron as well.
Oh, yeah. Yeah, so the question was looking at the serpentinized periddotites. I guess effectively they use them as architecture stones, but do you see that the reaction happening all the way to completion?
They're pretty. Do they get like not pretty? Do they weather the whole way through?
Yeah, all right. So do they weather the whole way through? The answer is yes. So folks after me have actually looked at these things to calculate a rate of reaction. So oftentimes, they see these things. If you look at a rock on the surface, basically it's all grungy looking brownish rock, but it's the road cuts and the quarries that they see this expose and happen. And I mean, even over the course of 6,400 years, you actually see this process happen. But you know, it all depends on how fractured the rock was in the first place, because, you know, you need a fracture, you need groundwater to get in there to react to it. So, I mean, it goes across the board. There's a lot of fractures, there's a lot of rocks, but, you know, there are cores that are probably, you know, as big as a few feet or so.
Yeah, you have to look at the chat because there's all kinds of thank yous and compliments. So good job. And we have thank you all for coming here. Don't forget to sign in and take a look at some field guides if you want to take some home with you. Next month, we have our final presentation of the spring season.
Oh.
So we look forward to seeing you all then again.
All right.
Thanks.